In the last video, we only basically used the built-in functions of the language. Oh, sure, we defined our own add, but it was just plus, and we defined our own add3, but it was just add3. Let's define our own functions that are pretty much just our own functions, nothing outside, such as the church numerals. So the church numeral for 2 is a function that has 2 arguments, and calls the first on the second twice. So f(f(x), with the parentheses being very important, because just like lambda calculus, applications bind left to right. So we don't want this to be f(f(x), because then that would be f applied to f. We want this. And I could also do the church numeral for, say, 3, which is fx, ff, fx. But of course, the church numerals on their own are sort of not that interesting, so let's go ahead and get multiplication as well. M, N, F, M, N, F. This was the definition of church numeral multiplication straight out of Module 2. And do they work? I want to multiply 2 by 3. Well, I mean, kinda. What this is saying is, I don't know how to show something that looks like this, and indeed it doesn't know how to show something that looks like that, because remember, a church numeral is a function. So let's see if we can figure out a way to show 2. Church numeral 2, we can't even show just that, because a church numeral is a function. But what that church numeral ultimately is a 2-argument function, in which the first is called on the second some number of times. So, knowing how currying works, I can use +1 as the first function, 0 as the second. Now I'll just get 0, and I'll add 1 to that as many times as there is the number. So, the church numeral 2 is indeed 2. This is also showing the big difference between the kinds of numbers we built in Module 2 and the kinds of numbers we built in Module 3. A church numeral is a number. It can store everything you need for a number. It behaves like a number. But it's a little bit unsatisfying because ultimately it's just a function. It shows us that functions are as powerful as numbers, but it doesn't let us show a number. It doesn't let us print a number in a convenient way. Whereas by using +1 as a function and 0 as a value, I can convert this kind of number into the numbers that we introduced in Module 3, primitive numbers. Now, finally, I can get up to here. Church mul of church 2 is a function. Church mul of church 2 of church 3 is also a function. It's a function that happens to be a church numeral. So I can take the same steps to turn a church numeral into a primitive number, and now we have that 2 times 3 is 6. I could even go further than that. I can multiply the multiplication of that by 3 and output that value. And if I introduce exponentiation as well, if I can type it. So this was our definition of exponentiation in the eta reduced form. Let's do something crazy. Let's take 6 by way of 2 times 3 to the power of 18, which is going to be a pretty big number, and print that out. And it'll take a while. It'll take quite a while to get 6 to the power of 18. Oh no! Okay, stack overflows are actually pretty rare in Haskell, so proud of myself. Let's do something a little bit simpler. Let's take 2 to the power of 18. It ought to be able to do 2 to the power of 18, right? That's not too big of a number. There we go. That's a paltry 262,144. I am impressed with my ability to get a stack overflow in Haskell. That's actually really hard to do. Anyway, so these church numerals behave like church numerals. All of the functions behave as you would expect. But they're not numbers, they're church numerals, so to get back, we have to, well, treat them as church numerals. Pass in a function and a value, and let it turn that into a primitive number. And the thing to notice here is how functions behave. Church mul, and then I passed it a function, and I passed it a function, and church mul returned a function, and I passed that a function, and that returned a function, and I passed that a natural number, and finally it gives me a primitive number as its result. But church mul isn't written as a 1, 2, 3, 4 argument function. Church mul is a 3 argument function. So how did it turn into a 4 argument function? Well, because one of its arguments, actually both of its arguments, in turn take functions as arguments. So if you work through what this actually returns, this returns, well, a function. And it's sort of difficult to distinguish between a function that's actually written to take 2 arguments, but then return a function that takes an argument, and a function that's written to take 3 arguments. Or in this case, a function that's written to take 4 arguments, versus church mul is actually written to take 2 arguments, but then returns a function. You see, there's this equivalence between returning a function and taking another argument. Well, in functional languages, that equivalence is very intentional. They are the same. From outside, you can't tell that church mul is actually a 2-argument function. And this style of thought, that returning a function and taking another argument are the same thing, just to be clear, it's not that they are somehow equivalent. In functional languages, they are the same thing. That style of design, this idea of returning a function and taking an argument being the same thing, is critical to how functional languages work. And that's why you get this kind of a style, where a 2-argument function is a 1-argument function returning a function, and you just can't tell the difference. That is an intentional design choice to make these two concepts equivalent.